Okay, so all right, so what I was going to go over, initially I had a fairly narrow thoughts about this that I would just go over like one paper, but as I kind of dived into it and followed the different paths, it seemed like an overview would be make more sense. So we'll touch on a number of different papers. We won't go in real deep. I'll try to just give the essence of the papers and then provide links for all the content, okay? And this has been a real learning experience for me. So if anybody else has, feel free to speak up and correct me or jump in and redirect if needed. So, all right. So the agenda, I thought I would start with just to get terminology right. What is fine tuning? What do we mean when we say that? The starting point for me, I don't know if it was actually the original the origin of these parameter efficient methods, but I kind of went back as far as this original paper that predicted the suggested the adapters, transformer adapters. So I'll start with that, and then we'll kind of come forward. As mentioned, there's going to be two sites that kind of drove my exploration. One is the AdapterHub. We'll go into the paper that started that, and then the other one will be the Hugging Face, and they have entered into the game as well. So I covered a little bit about what that and see what it means. I had raised the question in the beginning. This seems super cool. How come I haven't heard more of it? Because some of the stuff, the original paper is back in 2019, I think, which is ancient in machine learning timescale. I may have answered a little bit of that as we got further along, but anyhow, we'll explore that. And then there's some place we can dive in as deep as code if we want, just to see what it looks like to use and to also what the implementations look like inside for a couple approaches here. Okay, that makes sense. And then I had, so this is just my free time here. I don't want to kind of debate them, but my interest in this was kind of motivated by a few points that I'm thinking large machine models or large language models need to have. And one is that, one parameter set that does everything doesn't make sense to me. It seems like you're going to have specialization, modular skills that you can do with respect to the knowledge that goes into it, I feel like. And that first bullet, by the way, is kind of what we'll be addressing in this talk. Modular knowledge meaning more just static content. What's the news today? What are the contents of Wikipedia, et cetera. I'd be able to use tools. We saw that with Toolformer. And then online and continuous learning is something I haven't seen yet, but another area of interest. So anyhow, so this modular expertise capabilities is the part we'll be looking at today. Okay. So what is fine tuning? Basically, this has been around for quite a long time, and people have been using it. The idea is that you start out with a model that has been pre-trained on some function, some capability, some task, and that you change it. You now have a new task that you want to do, and rather than start from scratch, you take the old weights. You maybe swap out the output layer, but if the range has changed, I guess. So like if you used to classify 2 things, now you're going to classify 10 things, you have to change the top. You also might need more layers that are kind of randomly initialized at the top. Often you will start with a training of just the output layer with everything frozen, and then sometimes you'll gradually either start, once you've kind of done your initial training on the top layer, you'll unfreeze the other layers and do the whole thing, or maybe you might unfreeze just a few of them or gradually progress through them or whatever. And then you're just doing basically our standard gradient descent on this with parameters frozen at different levels. When you're done, you have a new stack, a full parameter set. You save that away, and that's your new fine-tuned model. Does that make sense? Any questions on that? Okay, thumbs up. Good. Okay, So this is the paper that started, Polsby started in 2019, introduced the idea of this adapter. So we don't have the transformer model, but if you remember, there's kind of an embedding. So if this is in a, let's say it's in a decoder only model, you have your embedding, and then you have your blocks, transformer blocks going up, and then the output layer at the very top. And this is looking at each of those blocks. So we'd see the normal multi-headed attention that you would have. And then you have a feed forward layer. Let's see, feed forward here, I think. Those would be the standard ones that you'd see. So the cross attention and the feed forward layer are the ones you'd be seeing in a transformer. And what these guys are doing is he's sticking in line a little adapter model that basically, it has a skip connection so it can do nothing easily. And then inside, he's got a little network that can take the embedding at whatever layer. At the beginning, the embedding is the token embedding, but as it goes up, we don't, who is it? It's the hidden layers, essentially, as you go up that residual chain. So it takes that hidden layer, allows you to modify it with a network that's got a bottleneck in the middle. So it's a smaller, what would you call a hidden state between these two. And that basically allows you, so you set that up, you set it to be, this to be a unity transformation. And then you essentially, again, freeze everything except these new pieces that you've inserted and run through standard gradient descent and fine tune that. Does that make sense? Grant, that looks a little bit like a question there.
Sorry. Where does it go in the picture? Or have you gotten there?
I wished I had a picture of
Okay.
Of a full transformer, but basically, right? Actually, there might be some down here.
It's okay.
Okay.
If you'll get there later or something.
No, here we go. So this would be the C of the Holsby architecture. This would be your key value query, your attention block in the transformer. Do you remember what the transformer architecture looks like? Okay, so this is repeated over and over, right? And you have your attention, and then this one right here would be your feed forward network, which is where when we were exploring Rome, if you recall, we were looking at the feed forward network and trying to understand, where knowledge is stored, and we said that it's in there. So this pink stuff is the stuff that gets inserted just above the attention and just above the feed forward network.
Interesting. Cool. Yeah, thanks.
Hey, Roger, if you go back to the original picture.
Yep. Which way am I going here? Okay, how do I see direction on here? Okay.
Yeah, this one, yes. So I think, yeah, I think it shows there that adapter that you show from bottom. If you go up, multi-headed attention, feed forward layer, and then adapter. And then that adapter is what is going up. And then again, it goes to the layer norm and 2 times feed forward layer and then adapter. So that's
right
where it is inserting. Now in the original transformer layer, and maybe I'm forgetting, I don't know, this feed forward layer, is it there right after multi-headed attention between layer norm and feed forward? I wasn't aware.
So I think this,
there.
Yeah, when I was looking at this, it was throwing me off a little. The feed forward layer here, part of the multi-head attention is you have your, your key value query, and it goes out and then it comes back together. And then they actually run it through a feed forward network before it goes back to the stream, the residual stream. So that's the feed forward network. What we looked at in Rome was this feed forward network. That's where the information was stored. And they're calling it 2x feed forward. Well, it does have, if you remember, that network kind of fanned out. It's a real big intermediate state and then fatten back into the embedding space or the hidden size. So I think so these two gray pieces are the pieces that were normally there in a normal transformer.
Yeah, so
And now when
in multi-headed attention, so let's say you have 8-way attention, okay? The typical setup, it's not required, but typically what you do is you split it into eighths, right? So if your regular dimensionality is 8,000, then you just do dimensionality 1,000. So each of those heads is operating in dimensionally 1,000, okay? And once you're done calculating all 8 attention heads, you concatenate them, okay? But when you concatenate them, you are literally forcing head 1 to be the first 1,000 floats and head 2 to be the next 1,000 floats. And that's not necessarily what you want, right? So that's why there's a projection matrix at the end. They call it an output projection. It's a single layer, okay? So it's just a single matrix multiply. And that, if nothing else, it could just be a permutation matrix, okay? So that would allow attention, head 1, if it's got 1,000 floats, to spread those 1,000 floats anywhere on the residual stream it wants, right? It doesn't have to be a permute. It could also, have non-1 values, right? But simplistically, it allows it to work on any subspace of the residual stream it wants, not just the first 1,000 hard-coded, okay? And so people don't really talk about that, but that is one of the required things in multi-headed attention, is you just have that output projection, they call it.
thank you, Ted.
And yeah,
That's
and
awesome,
then
Ted.
yeah, and then Dave, you're correct. The adapter then is just represented here. And then expanded here. In this case, there is 2 feed forward linear layers, but instead of going, whereas over here in the normal transformer, it gets very wide. In this case, you get down to a very small dimension in the middle.
And if I'm not mistaken, this parameter efficient transfer learning is training only this yellow box, right?
Yes,
After
yeah. When you'll
okay.
do a standard training cycle, but all of these other parameters will be frozen except for the ones that are in the adapters. Yeah.
Yeah,
So
I think
that was the Holsby model or method. In all of these, go ahead.
Sorry. Yeah. So the skip connection, they've shown it both on the left one and inside the adapter. I think there's only one, right?
No, because I think there's
2.
No, I think there is, because the normal architecture would have a skip connection.
Oh, I see.
And
I see. Yeah.
In this Holsby, they're adding the adapter in line after let's say this feed forward.
Yeah, I see.
So
I see it. Yeah.
Yeah. This guy makes it easy to do nothing, basically, right?
Okay. Okay. Yeah. Yeah. Yeah.
And then the weights can tweak it.
Yep.
So.
Yep. Got it. Yep. Thanks.
Okay. And what they found was that, training the adapters. So this is normalized. The y-axis is normalized by full fine tuning. And they found that, the performance is going to be comparable to fine tuning. And I think what they said is they are, as the model gets larger, if I remember, that it is, now actually this is a, the model, actually I'm not sure what this number of trainable parameter task is. What I got out of it is it's comparable in terms of performance. You can achieve the same performance, but I can't tell you what this one is. Okay. I did one of the ways that they measured it, and do they say it here, performance on the 9 tasks from the GLUE benchmark. So I just did a quick look at what is the GLUE benchmark. I've seen this come up a few times. And it's just a number of different natural language tests. They're relatively small, it looks like. So a fairly simple and standard test.
So did they use different number of parameters?
I'm sorry, what?
Yeah, I was wondering if they use different number of parameters for the different tasks, which is what you see in the previous figure.
This one?
Yeah.
I think that's so. If I understand this, they have maybe different models or of different sizes, and with fine tuning, the number of parameters that you need to fine tune is 10 power 6, 7, 8, or whatever, and the accuracy delta is low to begin with, or negative in this case is what I'm assuming. Negative. I'm assuming it's below 0 is negative. Versus if it is the adapters, then the number of parameters that it needs to train is lower and the accuracy is pretty high. So when fine tuning, you have to fine tune all the parameters and use, and this is a big model, or these are big models. So I'm assuming that's what it means. But is that correct understanding, Roger?
Yeah, you could be right that it's kind of like this is fine tuning of a large model. So it kind of corresponds to this one out here type of thing. Yeah.
So Roger, I think that the blue dots represent fine tuning, and you can choose how many of the layers you want to fine tune instead of fine tuning the entire original model. Okay. And that's where you get the different dots. So the one on the far left is you only tune, like, say, one layer, and then you tune 2 layers, 3, 4, 5, 6, 7, 8, 9, 10. And so
I'll buy that.
You don't get great fine tuning performance if you only tune 1, 2, 3, 4. But you can see as you get to around 8 or more, whatever, then it's pretty good. You don't necessarily have to fine tune the whole darn model. Okay. On the orange line, I'm assuming then that the number of parameters is a function of what your hidden dimension is.
This new
that thing that has the 2 circles, the vector that has the 2 circles right in the middle of there. That guy,
which also relates to these 2 green things.
Right.
So project, down, project. Yeah.
The smaller that is, the fewer parameters you have. The larger you make that, then the more parameters you will have, and that's why you have different of the orange-brown dots. That's what I'm guessing. I haven't read this paper.
Thank you, Ted. I think that's a really good interpretation. Yeah.
And so in this case, they're not really talking about fine-tuning performance overall. What they're doing is they're comparing fine-tuning performance to compute budget. Okay, so that's why the x-axis is number of parameters. So they're saying that, hey, even though we have far fewer parameters than fine-tuning all the top 12 layers, we get really great performance, as shown by almost the entire orange line. Even the far left one is pretty darn good.
Yeah, I think it's not. They make a point a number of times that the adapters have a much smaller parameter count.
Right.
It's still, to train these, you still have to do a lot of forward pass on the whole model, even if you just got a small parameter count. So it's not so much about the compute. The compute is better, but it's not as dramatic as the difference in the parameter size. And what it means is that if I have a task and I want to distribute a new task, I can do it with a much smaller parameter set if I'm doing these adapters as opposed to fine tuning. And also even if I have, if I have one machine that's doing different models, different tasks, loading in a new task just means I need to load in a small fraction to do task A versus task B, a small additional fraction. And so the point is, it's about the storage of the storage and transport of the parameters as much as the performance tuning. Does that make sense?
That's the big picture. Why I'm just saying how you get the different data points is by using larger hidden dimensions.
Yeah. Yes. Agreed. Yeah.
So for the case that we've already trained the model for existing parameters and we want to add new parameters, can we kind of we have a trained model for those previous parameters, and we kind of combine train the new parameters with another model, with another neural network, and then combine them together? Would that be an efficient way, or that would be not?
Yes. Exactly. And if we get to the end, we'll see the code that does that. But you're exactly right. And then you say, load a pre-trained model, and you say, okay, I want an adapter of this style and this size. And then I go through and just do a standard training on it. And kind of all the magic happens behind the scenes. And then when I'm done and I save it or push it, it'll just push my small subset of parameters up to, to the hub instead of pushing the entire model. So.
Thank you, Roger.
Roger, can I go back to one of the questions that Jayant asked a little earlier? It was in the picture before this, in the slide before this. So this residual inside the adapter, I have and I haven't read the paper, but I believe it could also be to avoid the potential, what is it called? Catastrophic forgetting, or I forget that, when they forget what the original network knew. So if the residual was not there, then it might forget the original tuning was there, original purpose of the network, but it may remember only the fine-tuned network. Yep. So with this residual, it helps not only learn whatever you're fine-tuning it for, but if there is a task which is not just part of the fine-tuning, it will not forget that. I'm assuming that's one big purpose of this residual.
Yep. Okay, so there was, going through time, there's a sequence here in 2020 when, so Pfeiffer introduced a slightly tweaked version. I'm not going to go into this too much, except that in this model, it was for translation. So he said, well, another place you could modify this is just by changing the embedding on the input side and on the output side. And so he had another similar parameter efficient fine tuning using that. But then he also that year published a paper that proposed this AdapterHub. So the idea being that there is, once we now have this standardized way of having this incremental, specialization, having it something that you can, a big benefit is the ability to trade it and download it, whatever. So he proposed coming up with a hub that would allow you to download the pre-trained model, the large model, add the adapter, train the adapter, and then push that adapter up to a common, common site, kind of a GitHub for these adapters. And that's what this paper was for in 2020. And then, so that's, it's AdapterHub.ml. I should have listed that on there as the site. That's where a lot of the information about how the adapters work. So this site basically, the way they did it is they cloned the Hugging Face transformer library and then made these hooks in there that allowed them to insert these little subnetworks in the residual stream. He also, from his tests, found that inserting it just in the feed forward, just after the feed forward, was sufficient. In that particular example, you didn't need to use both after the attention and after the feed forward. The initial paper referenced just these two methods, but they started adding a bunch of additional methods that we'll go through in a second. Okay, so one of them, LoRa, which stands for low rank adapter. It's basically a matrix that has that really skinny part in the middle. And the original paper did that is only on the attention, I think it was the key query and value. In there, they essentially put in parallel with the standard matrix that you would have, the linear transformation. They put this low rank transformation in between. Essentially what this does is the low rank allows you to go from the same, these dimensions, this is a square matrix. So whatever the input dimension is, no, that's not true. Okay, it is square and then they parse it up into the multiple heads afterwards, but in this case, you can emulate that same, n dimension to n dimension transformation with 2 matrix multipliers. You go in, you get smaller, and then you expand back out. So I was confused a little bit because originally, I guess I'd seen this associated just with the attention. But then it was pointed out that, okay, even though the original paper only had an attention, the methodology of doing this decomposition, which makes it a very small intermediate stream, can be applied at anywhere essentially, and whether it's the embedding, the attention, or the feed forward. Another model that got added was prefix tuning. And this one, actually, I didn't realize, I thought they just had done this similar type of add this parallel adapter matrix on the side of the key and value. But it turns, and that's what this picture looks like, but it turns out that it does a different modification. So instead of modifying the weights in the transformer, where you would freeze the original transformer weights and just train these little additional parameters that you've added, instead, what prefix training does is it leaves the entire model intact, freezes the entire model, but then back projects into the key value, what do they call them? Last key values. So it's essentially going back, you got the stack of hidden values that you can pay attention to, all the layers can pay attention to. What it does is it puts a couple stacks of those keys and values in front of your prompt. And those are not, so normally the input to these, so think of each of these boxes as a stack of hidden states that go up, right? So 12 or 96 layers deep. And normally what would happen is this text would come in as a token and it being embedded on the first one, and then it'd be modified as it goes up, modified by the multi-head attention, modified by the feed-forward networks until it gets the distribution of the predicted next token that you would have at the top. But this initial level is constrained, and all the other ones are a function of the feed-forward and the cross-attention modifications to that embedding. In this case, what they do is they make these, they call them like virtual tokens. They're free parameters, so they can take on any value, and they propagate. The loss function propagates the gradient back into these hidden states. And then when you go to use it, you just load that up as the previous hidden states. And I think it's actually the key values. You propagate it back to the key values, and during inference, those will kind of steer the output of these other stacks to the desired objective, whatever your new task is. That was a little complicated for me, so I'm open to questions if that didn't fit.
Hey, Roger, these white boxes that you have inside the gray box, that's the original transformer. And are these the layers of the original transformer, or are these the heads in the MHA?
So I think each one of these represents a stack of hidden states. So it would start as the name comes in as a token, gets embedded at the bottom. And then there's a stack of these, each of these. So it's not just the embedded token, and it's not just the embedding. It's actually the entire, all the states going up. Does that make sense?
So
I wish I had a picture of a transformer.
Sure, no worries. So each transformer layer is MHA, a layer norm, MLP layer norm, right? That's one transformer layer.
Yeah.
And then you stack those and you get 12 of those, 6 of those, depending on, yeah. So the one on the left is one transformer layer. Yeah, exactly. That's what it says, transformer layer, right? So that white box is one transformer layer, or
yeah.
Or
Yeah, for the one
okay.
token. It's all the ones driven by
If-
the one token. And my point
if I
is,
can jump- If I could jump in, I don't think it really matters whether you think of that as one layer or as the entire stack, because they have the same shape either way, right? One transformer layer has hidden dimension input with whatever the max sequence length is, and the exact same shape on its output, and a stack of 12 of them has hidden dimension times sequence length as input, and the exact
it's the same size all
as
the way up.
output. So
Yeah.
Dave, whether you think of that as one layer or possibly multiple, it doesn't, I don't think, conceptually change things. So it
And
might
I-
be simpler
Yeah,
for you to think of it as just one layer initially.
So this is one layer. Then these are attention heads in some sense, right? These white boxes.
Yeah, so I
Heads,
initially,
those are token positions. Those are full.
Oh, just the token positions.
It's-
Got it.
I originally thought of it as
Hmm.
kind of being these hidden states all the way up. But actually, having read through the paper and just think about it now as I use that term, it's really, remember we talked about that optimization with transformers where rather than recompute the attention keys and values, if you're adding one more token, rather than recompute it for all the first part of the sequence, what you would do is you would cache, you would save the key value from the previous tokens, right? And then you could just reference them without, the most recent generation of the most recent token or next token, prediction, next token, can just reference the previous keys and values without having to recompute the previous keys and values. Remember that? So that actually, now having read how this works, that's the more accurate way to think of what these are. These are the stacks of keys and values for all of the previous tokens. That makes sense, Dave? And then what
Yeah.
they're doing here is they're adding on some prefixed token or prefixed keys and values that are not constrained by any real tokens underneath or any of the weights or parameters that were used to generate those. These can be anything they want to be. And that allows these guys, because each of these will attend to the whole all the way across, right? If I'm generating coffee, I'm going to look all the way across, and I can attend to these prefix virtual tokens, and that can steer me in the correct direction.
Got it. So for simplicity's sake, if you assume that this transformer was 11, the sequence max length was 11 tokens, let's say. So
Yeah.
for this, the original transformer is now trained for, let's say, 9 or whatever it is, but they are prepending 2 tokens to it, and now it's the 11 token. So it will attend to all 11 during inferencing or during fine tuning.
Right, right. And these virtual tokens out here, again, will kind of guide it to whatever this new task is. And these have been trained by back propagation.
Fine tuned during
Yeah, during
these are
fine
fine-tuned,
tuning,
right? These.
during fine tuning, the rest of the transformer is frozen. But what isn't frozen is these key value states that are coming from the prefix.
So my only question with this one, and Roger, this is a little detailed question. When we train the transformer, we assume that all tokens will be there during training, right? And during inferencing, you are using all the weights for all the tokens. When we prepend this, then we are extending the architecture to include extra tokens now than the original, let's say it was trained for 512, but now we are extending the architecture and then fine tuning for that. Is that what is happening?
Yeah, I mean, there's nothing that says these weren't generated. These are not generated by any of the weights in the transformer. So the gradient won't propagate back into the weights, right? They're just given parameters. And I think there's nothing. I think what you're saying is what does it mean to not have input tokens for the prefix? Is that kind of what you're saying? Is that's different than it used to be?
No, sorry, I may have confused everyone. So in the adapter, the previous one, we added vertical layers, if you may, for fine tuning. For this
Yep.
one, we are adding, let's say, we are making it more wide, if you may. Instead of 512 tokens with prefix fine tuning, the fine tuned transformer is, let's say, 600 tokens now. So we are fine tuning for a wider network, and versus
Yeah, I
in
don't
the
know.
adapter, we were.
I look at it as being more of a way of, even in a decoder only network, of conditionalizing the generation on something. In this case, the something fits the format of past key values, but not necessarily wider. If this, and you could actually have prefix and like one of the Holsby low rank modifications, where the transformer would have a copy of that on each one of these tokens. You would have a copy of those, small parameter networks, right? So the difference here is that we're putting it we're not fitting it into the architecture like we did with the Holsby. Here it fits into the architecture. It's repeated up for all the layers, and it's repeated across for all of the tokens. In this case, instead, we're just, I don't want to call it, it's not wider. It's kind of part of the input stream. But in this case, if you read prefix training, it's the full stack of key values. Okay, that makes sense. And here's the.
Yeah, it
sorry.
makes sense, except just and then this is again a detail. So if I look at if you go to the original adapter, the picture that we have been referring to, I don't know if it has the tokens there at the bottom, but maybe one more, sorry. No, the one in the beginning that you had, yeah.
It's pretty much the same thing, a little more.
Yeah, but this one here, right? So the tokens are the inputs below the transformer layer dashed box. That's where the tokens are coming in, right?
Yeah, well, initially they'll come in,
value,
go through an embedding layer, and come into the first block.
Right. Yeah, except for the first layer, that it's everywhere embedded, right? The first layer is going to the embedding layer.
Yeah.
But after that, okay. So if I look at this box, below this are the set of tokens, right? Below this are those 512 tokens for the sequence that is going in.
Right. And kind of, you could think of a stack of these for each one of the tokens. Yeah.
Right. And then it goes into the MHA, and MHA will take those 512 tokens and its whatever dimensions it is, and create, let's say, 8 heads, right? So, or whatever number of heads are there. And that's where we have the query, key, and value, right? Now, now what we are saying, if I'm not mistaken, below this box, instead of 512 tokens, during fine tuning, we are adding, let's say, 8 more tokens before that. Either that or in the, yes. Okay, go ahead. Yeah.
Yeah, we're actually not adding tokens, but remember how the multi-headed attention references previous keys and values?
Yeah.
That's why they're calling them kind of virtual tokens. There's not a token that feeds into the structure, but there are entries that are like the key values of previous tokens that are just parameters. We're just passed.
Which means that, let's say originally each of the, so let's say 8,000 dimension are mapped to 1,000. Let me try to think. 1,000 dimensions, right, for the QKV, each 8 of those. And they are all cross-attending across 512 tokens, right? So there are 8 heads, each with 1,000 dimensions Q, K, and V. And each one of those is attending to rest of the 511 tokens, right? Because we have said the token sequence length is 512. So where
For the
are
last
these
one,
new
yeah.
ones? Yeah, where are these new ones being prepended? And I'm sorry if everyone else understands, I can read that offline. Sorry, but
You know what?
I'm
A
still
better,
confused.
yeah, it's just this picture isn't helping. It might be Ted's picture of the matrix of transformers might help if we had that. I don't know if Ted,
So
you have
Roger,
that handy?
can I ask a question?
Sure.
So Dave, I have a question which might be similar to your question, but I'm just going to word it differently. Okay. So in the first adapter you showed us, the Holsby, it's very clear that we're inserting an adapter module in certain places. Okay. And those adapter modules, they have 2 layers. So they have 2 rectangular matrices of weights, and that's where the new weights live, so to speak. Okay.
Yeah.
Do you have, I don't know if you have the answer, but in this prefix, where exactly do we add the new weights? Do we modify the QK matrices, or where do they live? Do you know?
Okay. I think I know. And if you think of the parameters that we have right now, you're using the term weights, right? Because they're going to be in here, they're going to be a matrix multiply of some hidden state as it goes up, right? And each one of them will multiply, and then a state, and you multiply, et cetera. And when you're doing a Holsby type architecture, you can see that you're just kind of adding more parameters, more weights into the network. And now you're tuning just those extra weights that are in the network, but it's more or less kind of the same type of thing. In the case of, if we had the picture where we captured the transformer operating on a sequence, but the sequence that it's everything except the most recent token, it's seen already, right? So in those examples, we were able to do an optimization because we saved the key values from all the previous iterations so that we know all the key values for the other side of that, 2x2 or the n by n array of matrix of these blocks, these transformer blocks. That the number of entries in that was related to the number of previous tokens that we had seen. What we're doing is adding on the end of that, prefixing that history with some parameters that we can propagate the gradient back into.
Right. But you have to physically, literally put those parameters somewhere. And that's what I'm asking if you know the answer to is, where do they live? Do you calculate Q and K and then you just prefix it with some hard-coded numbers? Or do you do a softmax and then prefix it with some numbers? Like, at what point do you inject these numbers?
So I played with the Hugging Face transformers, and in their interface, when you go to do an inference, one of the things that you can do is pass it a structure that contains past key values. It's a standardized structure with 2 set of matrices for all the keys and all the values for the whole thing. And that can be, and you can generate that. You can also return it. There was a pull request for being able to return that, and then you can feed that in. Internally, they use it when they're doing, as long as the lower layer accepts these past key values, when they're doing generation, that's what they do by default. They will always just generate one token, add that to the list of past key values, then call it again, right, and generate the next token. So here's the token, new token, and here's the token we selected, I guess, and here's all the past key values, run it again, and we'll get a new set of tokens we can choose from and a history. So all they're doing is they're, I believe, adding this to that history of past key values and passing it down through the standard transformer interface.
Okay,
so zero
Roger,
change to the transformer.
Hey Roger, may I say something here? So I just asked Bing GPT as well, and I trust Bing GPT, let's say 98, 99% of the times with its responses. And what it is saying, and I posted that on the chat as well. So I'll read that the third paragraph. It says the prepended prompts do not extend the sequence length beyond the maximum length of the PLMs. Instead, they replace some of the input tokens at the beginning of the sequence. So, for example, if the maximum length of the PLM is 512,
I wouldn't say it replaces it, just it consumes some of those slots.
okay.
Yeah. Yep.
And again, you know, all the disclaimers about Bing GPT. So sorry,
Yeah.
If it is wrong, then sorry.
Yep.
Yeah, so
Okay.
so from your description, Roger, it sounds to me like we calculate queries, keys and values in the first layer, the first transformer layer. And then we know ultimately we're going to cache the keys and values. And at that point, the output of the key matrix times the embedding, that gives us our, I don't know what to call it, but hidden key value.
Yep.
Okay.
Hidden state. Yeah.
That it's not the same thing as the hidden state on the residual stream.
Right.
It's our hidden key values. Okay.
Yep.
That there we have some hard-coded values that we prefix. So there's no matrix multiply, no nothing. It's just learned values that we insert at the beginning of this.
Yes. Yep.
Okay. And so then for what Dave pasted in the chat, then if you have 10 of these, then that means that if your prior max sequence length was 512, now you can only enter 502 real tokens because you're using up 10 of them for these hard-coded things you're inserting at the beginning.
Right.
Otherwise, you'd have to change the architecture, which messes with things.
Yep. Right. So this one doesn't change the architecture at all, doing it this way. Whereas the adapters did, right? The inserted stuff into it. I guess that I'll say, yeah, it depends on the implementation. The only change they make is you need to be able to insert these passkey values and not generate, ones that haven't been generated. Okay, so that's prefix training. Yeah, here's just another one. That's the link to the paper that talks about prefix training. And the results showing that they're actually doing better than the fine tuning on these tasks. We see this some places where some of these guys, these tunable parameters, I don't know if this is cherry picking or reflective or whatever, but here you've got, fine tuning is these, here it's reflecting, Ted, what you had said, the two fine tuning. This one of the fine tuning, they fine tuned all layers. Another one, they fine tuned a fraction of the overall model. And then the adapters where we insert parameters multiplies inside of the transformer. And then up here where we just, we extended the passkey values with this prefix, very small percentage tunable parameters, but it's getting good results. I don't know why it would be better than fine tuning, but it's getting good results.
I mean, it appears more like that. It appears more like that in context training, right? Where you have given some prompts, like for these large models.
Yeah.
So in some sense, that is becoming the red circles of tokens that you showed there, right?
That's the same instinct I'm having, Dev, but I'm still stuck on Roger's last statement that doesn't make sense to me. That even if what you're saying is true, Dev, if we have good fine tuning with air quotes around the word good, it should still perform better if you're willing to pay the computational costs to achieve that. And so the conclusion I keep reaching is that our fine tuning is done poorly. Like we haven't figured out that in this transformer large language world, the correct approach to fine tuning. If you remember, if you go to kind of the transfer learning we were doing on the initial CNNs, right? There were all these different methodologies for fine tuning, and they really leapfrogged each other. Like when you went from one, there was like the cross path fine tuning, and then there was just the last layer. The beginning was just kind of the last layer fine tuning, and then there were the appending fine tuning methodologies. But the methodology itself had like, orders of magnitude of impact on the effectiveness of the approach. And so, sorry, again, what I keep going to is your last statement, Roger. I don't know why this is better than fine tuning, and my instinct says it's just because we're doing the fine tuning wrong.
Yeah, that could be. I think the fine tuning they did, I think, was their fine tuning. So it may be one of those cases where, that the authors don't work as hard on getting the prior art qualified.
Right, and I have 3 comments. So if you go back to the slide before that, before this one.
Sorry, Deb, you
Roger.
got to be aware. I pissed off a bunch of people with my comment too, though. So there's people that have their hands up too.
Oh, I'm so sorry. I'm not on my iPad.
Oh, and Ted, I pissed Ted off too. Yeah. I've said
Okay,
one thing this whole meeting, and I've got like, oh.
So should I continue or maybe raise the hand and whatever?
I think the hand goes first. Shulin, what, you had a question?
Yes, but actually, I think Giants and Grant are before me, so I can.
Oh, Grant's just goofing off. He didn't have anything to say.
But Jayant has had his hand up.
Oh, I don't see. Okay.
I can go. So I agree with Sally. I don't think they've figured out how to do the fine tuning in NLP, and there's so much change going on internally, with the adapters versus in the image world, where you're just lopping off one layer in the end, and so sort of minimal change. The other thing is that the puppet tuning, it's external to the system, so it's not changing like you said, it's not changing the system. Is external, and to me, it's like some sort of a puppet master kind of thing. It's got its long reach inside the model, and it's trying to change it to whatever task is in front of it, something like that. Yeah, that's all I wanted to say.
I actually agree. So I've designed something very much like the prefix training, and I tested it on my model. And what I feel is that yes, if we fix some of the kind of like, if we have kind of like a neural network for 2 inputs, and then we fix it with not changing its parameters, and then we kind of like using this model as kind of like the input for these 2 parameters unchanged, and adding more parameters in, there will be cases that if the first model is not generative enough, then it will result in that always when you're adding more layers, then you will find the generative ability actually decreases. So yeah, so this is what I find on my experiment. But I will say, but I feel that this prefix training, if we can ensure that like kind of like some of the parameters are trained well with this. So I'm not sure if this will be a good application for the large language model, but I think it may have some applications in the industry, because like for like process lines, it's kind of like it's always kind of like one process go after the other process, and usually you have kind of like combinations of different processes. So if you were to build a good enough model, kind of like to so I think that like for industrial processing, you could say that like because industrial processing is kind of like the physics for the phenomenon is constrained there. So if and processing is whole is kind of like a combination of different physical processes. So yeah, I think it will be. I don't know if I say it correctly, but I feel that it may have a good application in the industry, because like we speak now kind of training models.
That I can see how that kind of makes sense. In this case, in the case of the adapter, we didn't have to take away parameters from the full model that you do in fine tuning. You're tweaking some part of the parameters. So you kind of added capacity and trained the new capacity and didn't take away from the existing performance.
Yeah, and what I also find is that the combinations of the prefix of the set of parameters, if you want to use the prefix neural network, then you kind of like need to choose carefully what combinations of the parameters. Yeah. If you're kind of like, if two related parameters are separated into layers, then it may turn out that you are not have a very good performing model. That's what I find about it.
Makes sense. Ted, did you have one? You still have your hand up?
Yeah, thanks, Roger. So, so I'm actually going to agree with Sally, not disagree. But apologies to Dave, who was in a meeting with me yesterday and already heard me talk about this. But somebody asked about, for large language models, traditional fine tuning versus RLHF fine tuning, and I kind of had an aha, and I think this is I think this makes sense. But although it's named RLHF, so it has the name reinforcement learning in RLHF. Okay, there's really not very much reinforcement learning in the way they do the fine tuning with RLHF, right? You just basically have some examples that are good and bad examples that have different scores, right? And you use some algorithm like PPO in order to update the weights, okay? But the whole thing about like rewards and trajectories and all that kind of stuff, that really doesn't come into play at all in RLHF. So what I said last night is what's actually different about RLHF is that, let's say you have a model and you say, oh, I'm a medical organization, so I want to fine tune on some more, medical notes to make it improve. Our training of something like GPT-3, a decoder-only model, it's only got cross entropy as its feedback signal. So, like, the model was about to say the word big, and you tell it, no, you should use this medical terminology, and so you should use enlarged, or I don't know, whatever, right? And so the signal is basically saying, you have a 50,000 word vocabulary, bump up the weight on enlarged, bump down the weight on big or any other words that had high probabilities, and now back propagate that through 175 billion weights. Like, and then if what you really want is to like have a multi-token expression or something like that, it's like very difficult through cross entropy to get that sort of, multi-word, phrase kind of signal going back. That's where I think if you're using PPO to update the weights, you can update the weights in a different way than just with straight cross entropy. And so that's why I do feel like there are limitations on fine tuning with just cross entropy. And that's why I believe that the prefix, which is sort of like in context learning, right? It's basically like a hidden system prompt that you insert at layer one. It doesn't have an English equivalent. It's just a numeric prompt, at layer one. Yeah, it has the ability to sort of hit things, that cross entropy can't. And so maybe in the end, the best is to do a little bit of both, which is what they did with ChatGPT. They said, we're going to do some traditional fine tuning and we're going to do some RLHF fine tuning and get the best of both worlds. I don't know if that makes sense to you guys.
Yep. Sounds reasonable. Dave, you had one?
Just wanted to add to Sally's comment. So the only thing which I can think of why fine tuning here is not as good as the fine tuning that we may have seen in the past is the size of the model and how this huge dimension fine tuning behaves versus the fine tuning that we may have seen in the past, which were, let's say, a few million parameters versus this is several hundreds of billions of parameters, or whenever this paper was published, at least a few billion parameters. So maybe there's something that happens in terms of the space generalization for the specific task. Fine tuning the whole set of parameters is not the same, and we saw good results in the past, but those do not apply anymore.
Maybe we need like an attention model to direct our fine tuning to the right parameters.
So in all seriousness, Dave, are you saying that if they had fine-tuned on a much larger corpus for a while, maybe it would have worked well? Because then you would have a large enough corpus to update the 170 billion parameters.
Yeah, could be, but I would imagine that fine-tuning typically may not be bringing that large a corpus compared to the original data set. That ratio may always be the same. The only thing that has changed is the number of parameters for these models versus what we used to see 3 years ago. And how that dimension, multi-dimension space works, I don't know, but if anyone has better insights,
But I'm riffing off of what you said, which is if I only have 100,000 training examples for fine tuning, maybe I shouldn't use a fine tuning scheme that's going to update 100 billion parameters. I should do something like this prefix that has a small number that I can tune really well instead.
That's a good point. Yeah. So if that ratio remains the same, but the ratio of parameters has changed significantly, then the same techniques may not work.
Does the particle discuss anything about the coupling layers, kind of like how to kind of like put together all the pre-trained together?
You mean putting all these different methods together? Is that what you're saying? These?
Yeah. So like so this article, they use some prefix neural nets to make it more address. Do they have any discussion about like how do they put those prefix neural networks together, kind of like the coupling between all the prefixes?
My understanding is the prefixes are the coupling of the prefixes is defined by the attention mechanism of the transformer. So they have a parameter at each layer, a couple parameters at each layer, and those affect all of the attentions at that layer. If that makes sense. So.
Yeah, that makes sense.
Okay. Let me go ahead and scroll on a little bit. I'll try to get through at least this prefix training stuff. There's a few variants of this. So that was the original one, the prefix one. I didn't capture the date on it, but there's another couple terms that you come across, which is prompt tuning and T-tuning, and wherein in this model, the author felt they needed the expressivity of modifying the hidden or the key values at all of the layers in the transformer. That prefix spanned all of those. They came back, and I guess there was work actually going on concurrently because they referenced each other here, but they came back and decided that they could do the same thing without modifying all of the states. In other words, just by modifying the inputs, that they could have enough expressivity to guide the probabilities of the sequence out. So the difference between prompt tuning and prefix tuning is that prefix modifies the key values, has these parameterized key values all the way up at all the layers. In prompt tuning, it only has parameters at the embedding layer that feeds into the first stack, as it were. So it's literally an embedding that precedes it. Now, it's not tokens because they are parameterized. If you went into the tokens, it's discrete and less expressive, but they are after the token encode or token embedding. At that layer, they are tunable parameters, learnable parameters. And I think we'll have they achieve I think it's actually even better performance doing it that way. If you run across the term p-tuning is just like prompt tuning, except that instead of having just a learnable, a 2D learnable set of parameters, or I guess actually it'd be 1D set of parameters at that point, embeddings. Instead, they have an LSTM that generates, the p-tuning has an LSTM that generates those embeddings. I wasn't quite sure what fed into the input to the prompt encoder. Whoops. Input to the prompt encoder is a task name, and the outputs are task-specific virtual token embeddings that are passed into the large language model. So that's the difference. This is p-tuning. Prompt tuning is like a prefix tuning, but just at the very first layer. Does that make sense? Any questions? There's a good link on here if you want to read a little bit more about prompt learning versus p-learning, or prompt tuning versus p-tuning. I should differentiate this, by the way, because last time we had talked about like prompt engineering, et cetera, where you would put, remember, you put tokens in that kind of exemplars of how to achieve this task. Maybe examples of calculations, maybe examples of how to break it up and do chain of thought. This is different than that. So in those cases, number one, it's actually very expensive to have these each token, like in a GPT-3, each token requires a 1.2 megabytes of key values that it has to store. You know, so if you have a 500, that's a 1.2 megabytes. So it's like a half a gigabyte for 500 tokens. It's a half a gigabyte of data representing that first token. So that's one thing. And the other is it's a small number of examples, and you got to get those examples right. If you don't get the examples right, it can have a big shift on the performance. In these cases where you're doing prompt tuning and p-tuning, you're going to have these tokens on the front end, these virtual tokens on the front end, but you can feed it lots and lots of examples, and they're all being back propagated into that prefix. So it's a much more robust way to guide the task as opposed to prompt engineering. Does that make sense? Okay. Oh, Dave, you had a hands up? Nope.
It was in the it was in the context of previous discussion. That's okay. We can take it later.
Okay. I'm going to take one other point here about prompt tuning that's advantageous, and that is, since this is a set of tokens that just is associated with a sequence, when you're doing batch processing, you can have a bunch of different tasks represented in one batch, because each task is just that original prefix. So from an operational perspective, it's also nice. Okay. Let's see, additional architectures. These are just some more that are supported in AdapterHub. How are we doing time-wise? We're going to have to quit here pretty soon. I think I can get through just this one. We'll get through IA3, and then I think we can call it quits here. The compactor one, I actually didn't even dive into this one. I didn't get a chance to do this. They did some sort of more complicated inline modifier, network modifier like we've seen before. In the IA3, just down in this paper, what they did here is they didn't add new networks. So like in these other ones, we could see, a network added in parallel, like in the low rank. In this case, they don't add another network. They just use, so this is the existing feed forward. This is the existing attention models. All they did is add a set of parameters that modulate these intermediate states. So it's really small. And they found that to be quite effective also. I think I have a slide later on that shows the relative performance of these. And the uni performance parameter efficient, that's LT. What is LT? Learning transfer. is just a combination of them. They're just trying to say, hey, there's too many pieces to put together. We'll put these 3 pieces together and add a gating signal to them so it can pick the right one for the right task. And that's kind of the level of innovation there. Okay, here's the IA3 one then. So again, they've got, all they're doing is learning these modulators for the value, the key, and then also the feed forward, the middle layer of the feed forward. And here, I think they have, yeah, here's where we show the different number of parameters across the bottom, and then the accuracy effect. And this paper claimed that the IA3 just doing modulation was sufficient, state of the art, above like even the low rank that they were doing. And where are the other ones? Prompt tuning. I don't see full fine tuning in here, which is interesting. But anyhow, small count, high performance. This one I think is a little newer, and it hasn't quite caught on the momentum yet. Okay. So this, I think, was comparing this few shot that I just mentioned with the modulation signals, comparing it to prompt engineering. So where the prompts are actually embedded in the sequence. And again, just showing it's good with, what is that, 3 orders of magnitude fewer parameters.
And Roger, I know we're short on time, but that's cheaper in cost just because running an inference on these big models like GPT-3, GPT-4 is super expensive. Right, because prompt engineering requires no backprop, no Atom, no nothing. You just try a few different things at inference time, right?
Yeah.
But I get it. I mean, an inference can be pretty expensive. I mean, you're assuming how many trials it takes to get a good prompt.
Yeah, I see what you're saying. Yeah. So it's per example, I guess, yeah, I guess this is ignoring the training side of it. Is that what you're saying?
Or no, I mean, for that, it is training, it's fine tuning. But for the blue squares, if that's prompt engineering, then that's inference.
Yeah.
Or something.
Because the x-axis corresponds to inference cost, yes. Yeah. And so that's where, like I said, when you have a long prompt, I don't even know, I haven't figured out what the cost, no, I did one time, figure out the cost, making an estimate on GPT-4, what is it, like 25,000 tokens they can do now? And that was like 100 megabytes worth of key values. And it's really big. And so that's what would drive, well, this is just GPT-3, but assuming GPT-4 was, I've heard.
Okay. No, I mean, I get that these cool things that don't require very many parameters and are relatively cheap to fine tune. I get that they're great. I'm just not exactly sure how you compare it to in-context learning, which requires no training.
Yeah, it's the focus is on not the training, but the inference side of it. The cost at inference time. But I understand what you're saying. You're saying, what about the cost of training, right? Where does that go? Because there's no, on the one hand, the things like this TPU has a training cost and look very small inference cost. The in-context learning has no training time cost and higher.
I'm sure maybe the paper like explains what their assumptions are. I'm just saying, how do you compare the cost of prompt engineering unless you know how long the prompt is and blah, 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 right? There's just a lot of unknowns.
Yeah.
Sorry.
Okay, I was going to call it quits then at this point, because I think we are at 8 o'clock. Exit this. Grant, I just clicked turn off the speaker tools and it'll come back?
Not yet, because Grant still has to take control of your desktop now that you entered in the codes that he told you to do. So give him just a second.
Yeah, I think can you just like hit escape? Does that work? Or move your mouse to the bottom left of it.
There we go. There we go.
Okay. Yeah.
Okay. So
Glad I could be of use.
I have the rest of what I had was more about AdapterHub and Hugging Face, and then some code about how to use these guys, how to train them, some of the methods that they support, and what's deep inside of them. So I can say maybe 30 minutes more if we want that at some point. Or
Well, if my buddy Doug wants to come next week, we could do 30 minutes with him, and then your 30 minutes will certainly turn into an hour and a half anyway. So
yes,
That sounds like a good plan.
does that
Okay.
seem reasonable?
it does.
Yeah.